Okay, let's go ahead and come back together and continue. So what we are talking about is we're talking about networks. We have just defined isomorphic in an informal sense. The math sense is or not very difficult, but it's more technical than needed for today. So we're not going to discuss that. What I'd like for us to do is I'd like for us to talk through unsupervised learning. So thus far in class, we've talked about what supervised learning is. And supervised learning is where we have observed Y values as part of our training data. As we think about unsupervised learning, this includes regression and includes classification. Because with regression, we have a continuous Y variable, and with classification, we have a discrete Y variable. In the context, but there are problems that don't have a Y variable, or we don't have access to a Y variable as part of our training data. And we use the term unsupervised learning to refer to that. You can imagine that supervised learning is where we have X and Y. So the Y is almost supervising the learning process. Whereas unsupervised learning, we don't have access to a Y variable when we fit our model. And so our model fitting process is unsupervised by a Y variable. That might be a helpful mental way to think about that. The focus of next week will be on unsupervised learning. So you're going to talk about unsupervised learning starting on Monday. However, let's talk a little bit about this unsupervised learning in the context of network analysis. So what I want to do is let's go ahead and think about some different, some ways for us to think about unsupervised learning applications on a network. So we've already mentioned one. One might be what communities exist in a network. We generally think about people when we talk about communities. So we might be interested in identifying maybe a fraud ring. If I work for Venmo or I work for a credit card company or something like that, I might want to be interested in identifying what communities tend to exist and maybe identifying people who are shuffling money or money laundering or something like that. I might try and identify that. This is unsupervised because we probably don't have a training set, at least if we start out in this work. Like let's say I started working for Morgan Stanley in their fraud analytics department and they don't have any Y data like, yes, this is fraudulent. No, this is not fraudulent. Well, in that case, I don't have any training data, any Y training data. So I have to just try and detect this or feel this out. I might also be interested in looking at other things. So, fraud ring, this is commonly used to identify terrorist activity. If you look at communications among individuals and modes of communications and all that, maybe I'm trying to identify terrorist groups. Maybe if I'm working for Facebook or for Twitter or something like that, I just want to identify different communities of individuals who share common thoughts. So maybe these are groups of friends or groups of colleagues. There's no magical set of Y data that says these people belong to the same friend group, and so we can just predict ones and zeros with a logistic regression. But we can try and identify communities in a network using a set of other tools, and you'll talk about these tools next week. Dealing with this is going to be kind of our focus of next week. But this is specifically related to network data, so I wanted to call it out now. Another common application, this is related to the fraud ring, might just be general anomaly detection. So maybe I'm not trying to identify a fraud ring community, but I just want to identify individual fraudulent transactions. So I work for American Express, and I want to identify what transactions here are fraudulent when they come in. But maybe we are just starting the department and we don't have a set of training data, or we feel like our training data is so heavily skewed, like it's very, very biased toward one particular subgroup that we don't want to use it because then we feel like we're only going to detect fraud in that one subgroup of individuals. So we might use anomaly detection techniques to identify what are credit card transactions that are being requested or what are Venmo requests that are occurring that go beyond what the general pattern of things is. Again, there's no Y variable here, but this is something that you'll learn about a little bit next week. And these are examples of unsupervised learning problems that you'll frequently see when it comes to network data. So to round out our discussion here, I want to spend a couple of minutes talking about storage, inference, and visualization with network data. Storage. Storage is going to be really, really challenging because we're probably going to represent things, as I mentioned earlier, in an adjacency matrix. So let's say that I fit this, right? I have an adjacency matrix where I can store all of my connections with one another. Well, let's say that I'm working for Facebook. Every month, or in terms of monthly active users on Facebook, there's somewhere in the neighborhood of 2.4 billion users. So if I were to try and store this adjacency matrix, this is going to be a 2.4 billion times 2.4 billion data set, which means that there will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yes, there will be 16 zeros in this, at the end of this thing. It's going to be like in the quadrillions, which is a really big number. And that's going to be just our adjacency matrix for Facebook friends. And so that's going to be really challenging for us to try and store because this becomes very, very, very quickly, it just grows out of hand. The other thing when looking at this is it's incredibly sparse. What I mean by sparse, it's lots of zeros. I think that on Facebook, if I remember correctly, at least a while ago, there was a limit. You could have up to 5,000 friends. So that means that, like, even if you are more popular than me, if you are, if you're Jacob Kohler in New York, you're very, very popular and you have 5,000 friends. Well, that means that in your row or the row that corresponds to you, you're going to have 2.39999,500 or 5,000, whatever it is, zeros, which is an insane amount of zeros. So this is going to be a very, very, very sparse or essentially empty matrix, and trying to store this can be really challenging. Generally, so you'll notice on the top right-hand corner, the random distribution and the power law distribution, networks tend to follow the power law distribution. And I'll zoom in so that we can see this. So if we look at the degree of each node, as that degree K increases, there are very few people who actually attain high values of that. So Jacob is one of very few people who may have 5,000 friends on Facebook, but the vast majority of people are going to have probably fewer than 200 friends on Facebook. So this is something that's going to be very, like most people will have even more zeros than the number of zeros that Jacob has. So this is something to just be aware of. Storage is a big challenge. Commonly, what people will turn to is, rather than using a standard SQL database, I know that we haven't talked about databases yet, but people will commonly instead use a solution called GraphQL, which is better suited for graphs, aka network data. It's like a database that just handles this stuff better. So that's one challenge. The next challenge is inference. So when you're dealing with all of this data, generally by necessity, we usually have to sample. Because if I'm trying to calculate, if I'm trying to calculate something and I've got 2.4 billion times 2.4 billion observations, my computers probably can't handle that easily. So instead I need to sample. However, there are a lot of problems associated with this as well. If I sample by edges, if I sample nodes, so in the Facebook example, maybe I take 100,000 individuals on Facebook. So I take a random sample of 100,000. Based on the number of people on Facebook, I'm probably not going to end up getting a ton of people that are connected with one another. So I might get 100,000 people who are not directly connected to each other, or there's only a handful of people who happen to be connected to one another. So if I sample the nodes, then I'm going to run into issues with that. I basically lose the topology or the structure of that network. If I sample the edges, I run into other issues. So instead of sampling individuals on Facebook, instead, let's say I were to sample 100K friendships, the connections among people. But that also has its own challenges. So there are very different ways of sampling. So you generally don't do like a simple random sample or a stratified random sample. There are more complicated ways called snowball sampling or forest fire sampling that are more commonly used. We're not going to get into that because it gets complicated quickly, but effectively, like as you imagine, forest fire sampling is essentially you sample one person and then you sample some of their connections. And you sample another person, you sample some of their connections so that you can keep your random sample of some nodes, but you're also retaining some of that topology. You're retaining some of those connections as well, but that gets challenging. So inference is harder to do, and this is a very, very new area. For example, I have 2 dissertations listed in the resources, and one recommendation that I would make is to maybe check those out. The first chapter of each of those dissertations tend to be pretty good, and like one dissertation is about methods of calculating the average degree in a network or a regression coefficient on a network. Just because this is still so new, people didn't really care a ton about this until probably the late 2000s, just before 2010. There wasn't a ton of research on it. The last thing is visualization. And in a very straightforward way, if I have a network A, B, and C, this is identical to the network A, B, C. And so trying to find ways to effectively visualize this when we're dealing with tons and tons and tons of data is an important problem for us to tackle. So let's go ahead, shift from here over to the notebook. I pushed the slides for the spatial data analysis lecture. Thank you to those of you who DM'd me to remind me about that. Okay. So the Jupyter Notebook is pulling up here. What we're going to explore is the Network X package. So we'll do a little bit of work in the Network X package, where the Network X package is kind of the standard package that we use in the context of trying to work with network data. So go ahead and uncomment this. It should be relatively quick to run. So go ahead and uncomment to install and upgrade that. What you'll notice as that's running is we're importing network X, this network X package, with the alias NX. So we generally import it as NX. We're also installing and upgrading Bokeh, which is a type, it's a visualization library. We briefly discussed it during data viz at the very end. We can use it to build out interactive visualizations. So the first thing that I would like for us to do is go ahead and instantiate a graph object as G. So we imported network X as NX. So I'm going to instantiate my graph object as G. So I'll say G equals NX dot graph. Graph must be capitalized. And then let me make sure that this is working for you all. So have you instantiated the graph? Go ahead and respond to that. Okay, cool. So once you've instantiated the graph, what we want to do, this is just an empty graph. There's nothing in it. There's no nodes. There's no edges. What I want to do is I'd like for us to add an edge to that graph. And the way that you add it, there's a method that will add the graph for us. So we have this graph object. I'm going to add the edge by saying add underscore edge A, comma B. And what this will do is it's going to create node A and node B, and then add an edge between them. You want to make sure that A and B are strings. And then we can draw the network by saying NX dot draw underscore network X of G. So I'm getting a matplotlib deprecation warning, but it won't affect what we're doing today. So we've got a very boring graph here. We've got a node A and a node B. So you'll notice that there are numbers here. These numbers don't really matter because they're arbitrary. There's not something that A has to be at -1, +1, and B has to be at negative or at 1, -1. That's not something that has to happen. This is just a, the numbering there is arbitrary. So what we want to do is let's come up with a more complex graph. So let's add these different nodes and draw the network. So we've now added an edge between B and C. This also created a node C. Add an edge between A and C, and then added an edge between C and D, which creates a node D. We draw this network. What you'll notice is that in drawing this network, I have this image here, but you may have different edges in your network, or you may have a different visualization. And that's because all of these are arbitrary. There's no right way, or there's no one way to necessarily represent that network. Thank you, Jasmine. So let's do a couple of things on this network. Let's say that I want to get the shortest path between B and D. So I can directly get the shortest path by saying print of NX dot shortest path. And then I need to say, let's use graph G, and then let's specify nodes B and D. So this will tell me the shortest path from B to D, to start at B, go to C, go to D. The algorithm that is likely being used here is called Dijkstra's algorithm. It's, I then J, Dijkstra's algorithm. And I'll just drop that into the chat as well if you want to take a look at it. It's a way to find like the shortest path between two nodes. Commonly used to solve like the traveling salesman problem, which Michael from Boston mentioned earlier, the traveling salesman problem. A Dijkstra's algorithm or a variant of that is used to solve that problem. Basically, if you were a salesperson and you were traveling around, what is the best way to optimally hit all of the places you need to sell stuff at? If I want to get the shortest path length between B and D, I'll do almost the exact same thing. NX dot shortest path length G, B, and D. So it tells us the shortest path length. So we have to go from B to C, which is 1 step, C to D, which is 2 steps. I imagine that if I had to check out the documentation for this or the code for this, it says, what is the len of this minus 1? Because this includes the starting and the ending point, but there's actually only 2 steps. John from New York. So this length is the number of steps, not the actual distance between the steps. Correct. Here, I'm just saying the number of steps. However, there are other ways to go about this. So for example, you can specify weights for each thing. So if the distance between, for example, like if the distance between A and C was 10 meters, but A and B is 15, B and C is 20, C and D is 50, you can pass in those weights and it will measure that for you. So, and there are methods that will be able to handle that for you. But this length here is telling us the number of steps from one to the next. What you'll notice if I run this, I'm adding an additional edge between A and B, and I'm drawing the network. But Network X is a package that's not set up to do visualization super well. So here, there's an additional node between A and B, but it just gets drawn on top of one another. It is not magically tackled, or it's not designed to visualize stuff well. So we generally, when we want to visualize networks, have to turn to other packages, and we'll do that shortly. Let's fit the 7 bridges of Königsberg graph. So what I want to do is I'm going to instantiate a multi-graph object as 7 bridges. In order to instantiate a multi-graph, remember multi-graph means you can have multiple connections. Here I'll do nx dot multi-graph. Multi and graph should be capitalized. And then we can create all of these bridges at once. So I'm using 7 bridges dot add edges from, and I'm just passing in a list with tuples in it. So we're looking at each individual set of values here. So it's drawing 2 bridges between A and B, 1 between A and C, 1 between B and C, 2 from B to D, and 1 from C to D. I pass all of that in a list. I'm not certain what the output is here. I think it's counting the number of times that those 2 edges are connected. So for example, A to B we've got our 0th bridge, and then we've got the first, but we would think of it as our 2nd bridge connecting them. A to C is 0 because that's the 0th bridge. B to C is the 0th bridge. B to D is the 0th. And then the second, B to D, is our first. C to D is our 0th there. I don't know why it does that. Blake said if you run it again, you get a different list. So I would imagine, I haven't run it again and I personally don't want to, but if I were to run it again, I might imagine that this would be like 2, 3, 2, 2, 2, 3, 2, because you'd be adding these again to 7 bridges. So I think that it's kind of like above where we did g.add edge. You could just add a bunch of edges at once. And so if you changed this object, you use this method on the 7 bridges object again, you'd be doing this over and over again. So you'd be adding 2 more bridges between A and B, but I'd have to explore that to see. We can create our adjacency matrix for the 7 bridges problem. I'm going to do nx dot adjacency matrix. So nx dot adjacency matrix of 7 bridges. And if I run this by itself, we get this sparse matrix. So remember that our data is sparse. There's a ton of zeros, and it's compressed in a way that allows us to not need to save all of those zeros. So instead, what I want to do is I'm going to specify here dot to array, and it's going to take that and change it into an array. This is something that you may have seen earlier when we did count vectorizer, because there's a ton of zeros in our count vectorizer columns. So we set it to be an array. And this is our adjacency matrix. So A is not connected to A, but A is connected to B twice. A has one bridge connecting to C. A has 0 bridges connecting to D. This is our adjacency matrix for that network. If we want to check to see if each bridge can be traveled exactly once, the math term for this is called an Eulerian path. Remember that Euler is the person who discovered that, so we've called this an Eulerian path. Can you go across each edge of your network exactly once? And it's quite easy to do this. There's nx dot is, and there are many different things that we can do here. But I'm going to do is Eulerian, and I'm going to pass in my 7 bridges data. And it returns false. There does not exist that Eulerian path. Blake, is there any reasonable benefit to choosing dot to array instead of dot to dense? I don't know off the top of my head. I did both in prep for this lesson and set them equal, or I checked to see if they were equal to one another, and everything said true. So I'll be honest, I don't know if there's some hidden benefit. For a matrix of this size, it's not going to matter. But for larger stuff, I checked to see, I might time both of them and see if there's some benefit to using one. But in my experience, I haven't noticed a difference. So Josh and Noah asked the same thing. Is there a difference between ADJ matrix or adjacency matrix? I don't know. You could check that out and see. So if I were to copy this, add a cell, it looks like those are exactly the same. And if I ran this equals, and then change that to ADJ matrix, just to confirm, everything is truly the same. Jack from New York asks, what if we want to make a directional path? Oh, yes, John. So this is exactly what I did when I was comparing to dense earlier. I just checked adjacency matrix, double equals ADJ matrix, and then it says, hey, everything here is true. So those are exactly the same. And that's, kind of to Blake's question. I did the exact same thing with to array and to dense earlier to see if those were the same. Jack, if you want to make a directional graph, you have to instantiate directional graph. So it's nx.capital D under or lowercase I, then capital graph. But we're not going to do a directional graph in here. Another method, remember that isomorphic means the two networks are the same. So we can check if 7 bridges is isomorphic to G. So I'm going to do NX is isomorphic, 7 bridges, comma, G. And the answer is false. Those two are not isomorphic to one another. But is 7 bridges isomorphic to 7 bridges? Well, I sure should hope so, because graph should be equal to itself, should be isomorphic to itself. So is isomorphic, we'll test to see if your 2 graphs are the same. So there's a lot of different things that you can play around with in the context of network X. A couple of things that, or 2 last things that I want to show you. The first is, it's Kuratowski's theorem. So I took a class in undergrad called Applied Topology, which is a bit of a misnomer because there is very little that's applied about topology, or I thought so. It actually ended up being really, really cool. And there were lots of things. And in fact, this is a good example of an application of topology. So Kuratowski's theorem states that a network is non-planar if and only if a network contains K5 or K33. Well, what the hell are the words that I just said? So what I'd like to do is create this network called K5. And let's do nx dot complete graph 5. And then draw that network. K5 is the complete graph on 5 nodes. That means that there are 5 nodes. We see 0, 1, 2, 3, and 4. And they're all totally connected to one another. They're all completely connected. So 0 is connected to everything else. 1 is connected to everything else, and so on. If we want to draw this network in a certain way, visualization is a challenge. And granted, this is not a package, again, that's like set up to do visualization super well. But instead of saying draw network X K5, I can add an argument here that says pos equals for position nx dot circular layout K5. And what this will do is this is going to force all of your nodes to be on a circle around the edge. You could fit a circle through those. Could you? I don't know. That seems a little bit of a stretch, but that's going to better represent this because sometimes, depending on how you run it, it might be more compressed. By setting a circular layout, it forces everything to be a bit more visible. So that theorem above talked about non-planarity. All that means is that you can draw this without crossing over itself. If a graph is planar, that means you can draw that graph without overlapping itself. Your pencil would never draw over the same spot twice. With this, drawing network X, or with K5, it is impossible to draw this network in a planar way, like flat on a graph. So if you want to generate the complete graph, we've got this. And I'll share all of that code with you. So Jose asks an interesting thing. What does it mean for a graph to be non-planar? So let's say that you are working at or you're designing semiconductors, or you're designing like chips for computers. So, let's treat, my iPad as like a computer chip. Well, you need to draw certain patterns on it, and your patterns cannot overlap one another. So what that means is, like, if you're drawing like the little circuit board or whatever, your connections have to be organized in a very specific way, because if you happen to have this graph on my screen here where things are crossing one another, your circuits aren't going to work the way they're supposed to. So in fact, there's a ton of money and a ton of research into designing that sort of thing to avoid having K5 show up anywhere in your circuit board or in your chip. So if you have 5 different things on here, and if they're all connected, there is no possible way to draw all of those without having those connections overlap with one another. Where the money comes into play, in order to fit something like that, like in a factory, an assembly line, for example, basically what you'd need to do is drill a hole, or get a machine to drill a hole through this really thin thing and run that connection through to the other side, so you can avoid that. However, you think about the amount of money it would cost to generate a computer chip that is just everything's on one side, versus needing to drill a hole, make sure it doesn't break, run the connections through and all that. That's going to take way more time, way more energy, and way more money. So if you can find a way to design your circuit board so that K5 is not hidden somewhere in that, insert pentagram joke here, it's not hidden somewhere in that computer chip, then you might be able to save a ton of money in developing those semiconductors. The one other graph that is not possibly planar is called K33. So for K33, this is going to be nx dot complete multipartite graph 3, 3. This graph you may have seen before as part of the 3 utilities problem. I've linked that problem here. So let's say that nodes 1 or 0, 1, and 2 are 3 houses. 3 represents oil, 4 represents water, and 5 represents electricity. And there's, it's like a little game or something. It's like, try and draw lines like oil, water, and power lines to each of the 3 houses, because each house needs that. Try and draw that in such a way that that the lines don't overlap one another or don't run into one another. And it is impossible to do that. It's impossible to do that on a flat surface or on a plane. So we say it's non-planar. However, there's actually a coffee mug. This is not that mug. There's a coffee mug where you can actually do it on a coffee mug because it's not a flat surface. And so there is a way to do it on a mug. 3 should be Comcast, but we don't have time to get into Comcast today. The last thing that I want to show you is bokeh. So go ahead and run this cell. The only thing I want to do is instantiate the Karate Club graph object. This is a famous set of karate data, and it's commonly used to pull up or to try and detect communities in these individuals who are playing or not playing, we're doing karate together. So I'm instantiating this as a capital G nx.karateClubGraph equals G. And I've shared that code with you. And if we draw this network, which is still a relatively small network, it looks like there's only 34 nodes or something like that. That's relatively small in terms of how networks go, but this is tough to visualize and this is ugly. So let's clean it up. What I'm using is the bokeh library to clean this up. I'm creating a plot range. So I'm saying, how big do I want the plot? Specifying the X and the Y range, giving it a title. And I'm using the bokeh method from network X, bringing in my network G. I'm forcing it to be laid out in a circle, and I'm rendering this plot. So if you run that, there's nothing you need to edit there, but if you run that, we get this interaction or this graph. So here we've got all of those values. And so they're organized on a circle, which is a little bit better, but there's still a lot of mess here. So let's see if we can make additional changes to this. So we're going to run this next set of code, which is almost identical, but I've added in here, let's color the nodes. So I've added this bit of code that will allow us to color our nodes. And you see that we've got our blue nodes here around the edges. So those are a little bit more attractive. Continue scrolling down. I'm going to make an additional change to this, where let's also color the edges. So rather than having those super skinny black lines, we now have these gray lines. And again, our next step, the bokeh library can handle interactive things really well. So let's make it interactive. So I'm going to add here a bunch of tools. There's a hover tool, a tap tool, and a box select tool. You can learn more about this at the link here in terms of the tools that bokeh has to offer. And we have to set something in here in terms of when I look at items, I want to look at the node. When I select a node, I want to be able to also look at the edges linked to it. If I look at an edge, I want to also see the nodes that are linked to it. So this graph is now interactive. And you'll notice that if you mouse over one of the edges, it will highlight that edge and the nodes that are connected to it. If you highlight a node, you can say, based on that node, what are the other nodes that are connected to it? You can draw a box here So click and drag, and that will allow you to select some of those nodes. And you'll see how each of these are related to other things. So you can use Bokeh to make this interactive. And then the final piece, which is the coolest piece, is you can also export it. Oops, that went down. So you can export it as an HTML file. So you could put this on a static website. So if you import output file, the only thing I changed from this is down here, I'm outputting it as an HTML file. If you run that, this pulls up in HTML. And what you'll notice is that in your folder or in your directory, what you're going to be able to do is you'll see an HTML file there, which is really, really cool because now you can just save that HTML file and put it as part of your website if you'd like to do so. You'll be able to do this for whatever type of visual you want to do. So I'm hopeful that this code is going to be helpful to you. And by stepping through it, you see what each step is doing. Obviously, we didn't go in detail with all of this, but as you want to tweak this to your own, hopefully you will be able to leverage this to your own benefit. Jack from New York asked if your Python would have to be actively running. I do not believe it would have to be actively running because you're exporting it as an HTML file and you could just save it somewhere else. So your notebook shouldn't have to be running. CJ, can you do distribution of node degree? You could. In the time we have, I'm not going to be able to do that, but there's something in Bokeh called a tooltip where you could even, as you mouse over something, it can put out attributes. Like if you wanted to say, what's the degree associated with this node? It would say like 2. Or if you wanted to, there are different things that you can do. That's just not something that I included, but you could definitely do that. Okay, so that is intro to network analysis. What I want to do is, I know we've only got about 3 minutes left, but what I'd like for us to do is I'm actually going to have Tim join us. So Tim being our new global instructor, he is on camera as well. And so he's going to be able to chat with you for a few minutes. Tim, if you could just go ahead and introduce yourself to everybody, tell them a little bit about your background, and maybe like a fun fact about you or anything like that that you'd like to share. It'd be great for you to come on and and speak to everybody. So may I introduce Tim Book, our new global instructor. Tim, the floor is yours.
Awesome. Thanks, Matt. Hi, everyone. My name's Tim. Starting on Monday, I'm going to be the new 3rd global DSI instructor, so you'll get to know me plenty over the next few weeks. A little bit about me is I'm from New Jersey, born and raised. I went to Penn State, got my undergraduate degrees in math and statistics, and then I went to Ohio State for graduate school, just like Matt, which is where we met. From there, I came down to DC and worked at a small consulting firm called Summit Consulting. I worked there as a data scientist in their litigation analytics directorate. Our tagline was, we help lawyers win cases with statistics, but we really mostly just get favorable settlements. I'm excited to start with my first lesson. I'm going to be doing our first clustering lesson on Monday morning with K-means. I wasn't prepared with a fun fact. I don't know. I do have a fun fact. I am now the 3rd global DSI instructor with a pug. I found out. I know Riley has a dog that's like half pug. I do have 2 pugs. They're not with me here. They're at my parents' house. But so keep the pug memes rolling, I guess.
Cool. Thank you very much, Tim. Tim recently got his chair. So Brian from New York said eyes are squarely on that racing chair he's sitting on. So Tim, my understanding is Tim recently got that chair. So you will see a lot more of that starting on Monday morning. So I'm very excited about that. So with that being said, thank you all very much for your time and attention. This is the last lesson I've got this week. Riley will be here to chat with you tomorrow about Benford's Law, which is one of my favorite lectures to watch. It's generally a crowd pleaser. In addition to that, I will be back to chat with you about principal component analysis on Tuesday afternoon. So we'll have a little bit of a break from one another. But have a wonderful rest of your week, and I will talk with you all on Tuesday, if not sooner. So take care, everybody. Have a good one.